Hey, Table 5 here.
Hey.
Have you ever wondered why objects move the way they move? Some slowing down, speeding up, stopping completely, and start moving. This is Newton's second law of motion, the law of acceleration, where if you apply a force on an object, correct, the object will accelerate.
But diving deeper, we see that momentum is conserved. In other words, the law of conservation. The law of conservation basically states that when a force is applied on an object, that object doesn't lose that velocity or momentum, and it remains constant unless an external force acts on it.
There are two types of problems we use for the law of conservation on elastic and inelastic collisions. Elastic collisions are where the system has no external forces being applied, while inelastic collisions are ones where external forces are being applied. For example, when you hit a ball of billiards, that is an inelastic collision.
Okay, so what is momentum? Momentum is the vector of an object, more specifically, the mass and velocity of an object multiplied together, right? The equation for momentum is P momentum, right? Is equal to m times v, which is mass times velocity. This shows that it is directly proportional to mass and velocity, meaning that if you change either one of those variables, momentum will increase, and vice versa. So, what exactly is impulse?
Another aspect of momentum is understanding impulse. The equation for impulse is J, which J equals force times time, and force times time will equal mass times velocity. This equation can be simplified down to the impulse momentum change theorem, which shows that change in momentum is equal to the impulse.
What is the conservation of momentum? As we know from the law of conservation, momentum does not change in an isolated system. So this means during the collision, right, the total momentum before and after the collision, right, will stay the same. This equal. Alright, yeah. This means the magnitude of the forces before and after are going to stay the same, and they're going to be equal and opposite reaction as described in Newton's third law. Time for both objects will also be the same because they endure the collision for the same amount of time, right? And impulse is equal to the change of momentum, the change of momentum. So those two will be the same.
Momentum has two variables, mass and velocity. It is also a vector. In a momentum equation, P equals mv, P represents momentum, while m is mass and v is velocity. This equation shows that momentum is directly proportional to its mass and its velocity, meaning that if you increase mass or velocity, momentum increases. For example, an object that has a mass of 2 kilograms and a velocity of 2 meters per second, the resulting momentum would be 4. However, if you increase the velocity to 4 meters per second, the momentum becomes 8, because there is a direct relationship between the mass, velocity, and momentum. Another aspect of momentum is understanding impulse. The equation for impulse is J equals force times time, which is the same as mass equals change in velocity. This equation can be simplified down to force equals change in momentum. The impulse momentum change theorem shows that change in momentum is equal to the impulse. For example, if a 1 kilogram cart was pulled with a force of 1.5 newtons for 1 second, and another cart was pulled with a force of 3 newtons for half a second, they will both have an impulse of 1.5 since impulse equals change in momentum. The value of change in momentum would also be 1.5. As we know from the law of conservation of momentum, momentum does not change in an isolated system. This means that during a collision, the total momentum before and after is constant or conserved. This means that the magnitude of the forces before and after are going to be the same because it is an equal and opposite reaction as described in Newton's third law. Time will also be the same since the objects endure the collision for the same amount of time. And the impulse and change in momentum are the same as mentioned earlier, since impulse equals change in momentum. In the example shown before you, the total momentum before the collision is 14, and after the crash it is also 14, showing that momentum is conserved. The change in momentum is also 0, which proves that momentum is conserved in the isolated system. A 3 kilogram red ball moving 3 meters per second collides with a blue 2 kilogram stationary ball. Find the velocity of both balls after the collision. To solve these problems, we first need to calculate the red ball's momentum, which is 3 kilograms times 3 meters per second, which results in 9. Then to calculate the momentum of the blue ball, which is 2 kilograms times 0 meters per second since the ball is stationary. The total momentum is 9. Now to find the velocity after the collision, we know that the red ball's momentum will be 3v and the blue ball's momentum will be 2v. You then need to set the total of 3v and 2v equal to 9 since momentum is conserved and will be the same. After some algebraic calculations, the combined velocity is 1.8. To show the law of conservation, we need to find the momentum before and after the collision. Momentum is mass times velocity, so we're going to find the initial momentum and final momentum after the crash. The initial momentum of car 1 can be found by doing 0.334 times 0.6. This will give us 0.2064. To find the initial momentum of car 2, we're going to do 0.130 times 0, since the velocity of a still car is 0, and this will give us 0 as the momentum. So the total momentum before the collision will be 0.2064. Now to find the final momentum after the collision, we're going to do 0.334 times 0.4, and this is going to give us 0.1336. Now to find the final momentum of car 2, we're going to do 0.130 times 0.4, and this is going to give us 0.052. And the total of this is going to be 0.1856, which is very close to our initial momentum. Now to find the change in momentum, we're going to do 0.2064 minus 0.1336 minus these numbers, and we're going to get 0.0728. And now we have to find the change in momentum of car 2, which will be 0 minus 0.052, and this is going to give us negative 0.052 because forces act in an equal and opposite way as described in Newton's third law, and the total of this is going to be 0.0208, which is very close to 0, which is good. If this experiment was done in a perfect isolated system, then the P1, then the initial momentum and the final momentum would be equal, and the change in momentum would be 0. Since this isn't a perfect isolated system, it's not exactly the same, but it still shows that momentum is conserved.